These are the lesson activities for differential equations, lesson 1314. Recall our mixture problem from last class. The differential equation that models the amount of sugar in the vat at time t was ds dt equals 2000 minus 3s over 100, and the solution is s of t equals ce to the negative 0.03t plus 2000 thirds. So what happens to s of t as t approaches infinity? That is, find the limit as t goes to infinity of ce to the negative 0.03t plus 2000 thirds. Well, this term, as t goes to infinity, think about e to the negative t. The coefficients don't matter that much. Qualitatively, the graph goes like this. So as t goes to infinity, this term goes to 0. So my limit is 2000 thirds. Now, if we look at the slope field, what does that tell us about the long run behavior of s of t? So pick some initial conditions, like if we start with 100 grams of sugar, and follow the slope field, it looks like it's going like that. And if you start with 1100 grams of sugar, follow the slope field, it seems to be coming down like that. And this value that they're all approaching looks like it's about right here. And that is about 2000 thirds. That's 666 and 2/3 grams of sugar. So it does agree with the limit we calculated. Now we want to sketch a slope field for dy dt equals 2t. Draw enough tangent lines to get an idea of what the solution will look like, and then sketch a few particular solutions. So we need to make a little table where we have points. T and y. So I need t and y, and I'm going to calculate for each t and y, calculate dy dt. So we'll start with 0, 0. If you plug in 0 for t and 0 for y, dy dt, which is 2t, is 0. So that's a horizontal tangent line. So we have a tiny little horizontal tangent line there. And then maybe I'll do 1, 0. So when t is 1, 2 times 1 is 2. So at 1, 0, I have a tangent line with the slope of 2. And maybe I'll do one more on the x-axis, 2, 0, or sorry, the t-axis. So that would be 4, so much steeper. Maybe I like this one a little bit less steep. Okay. And then because y actually doesn't seem to matter at all in my calculation of the slope, it's just 2 times t. Y doesn't matter, so I can just move up and down the y-axis. I can just move vertically and copy my tangent lines like that. So because t is 0, 2 times 0 is 0, doesn't matter what y is. And then I can do the same thing as I go up and down vertical lines. And then these are steeper. Trying to make them all parallel as you go up and down the vertical lines. Okay, and then maybe I'll do -1 and -2. So you get -2 and -4. So something like that, and then steeper. So the graph is starting to take shape, and it kind of looks like a parabola, which makes sense because the solution to this differential equation is y equals t squared plus c. Okay, so what's special about this slope field, and what is it about the differential equation that makes it so? So the tangent lines are parallel along vertical lines. because dy dt depends only on t. Doesn't matter what y is. Use the slope field for dy dt equals 4y times 1 minus y to sketch solutions corresponding to these initial conditions. So y of 0 equals 0.5. So here's 0.5. If I follow the slope field, it looks like it goes up and levels off like that. And if I follow the slope field backwards, it looks like it approaches the x-axis, like that. All right, if y of 1 equals 0.5, do another color. Right there. It has a similar qualitative approach to, looks like 1, and then this comes down to 0. And then y of negative 1 equals 0.5. Starts there. So it looks like it goes up and levels off, and then comes down and levels off at about 0. What's special about this slope field? It's sort of the reverse of what was special about the last one. If you look along horizontal lines, the slopes are all parallel. So slopes parallel along horizontal lines. And the reason that is because the differential equation, dy dt, depends only on y, right? There are no t's in there, so the t value as you go left and right doesn't matter at all. Only the y value matters. Consider the initial value problem dy dt equals t plus 1 times y minus 2 with y of 0 equals 10. I've given you a slope field here, but I'm not going to draw on it yet. I'm going to jump to part A. What is the slope of the line tangent to the solution y of t at t equals 0? So I calculate that by looking at the formula for dy dt. I'm going to put t equals 0 in, right? So I'm going to put a 0 in for t. And then I have to put something in for y, and I happen to know the y value when t is 0 is 10. So I can put a 10 in for y. So that's going to be 1 times 8, 8. Now I'm going to use Euler's method with a step size delta t equals 0.5 to approximate the solution at 2. Okay, so step 0, I need my t and my y. That's my given initial condition, which is 0, 0, 10. All right, that was given up here. Y of 0 equals 10. Okay, and then I calculated dy dt at the point 0, 10. That came out to be 8. And then delta t is always going to be 0.5 because I was told to use that as my step size. And now I can calculate delta y, the change in y, by doing the slope times delta t. So my slope is 8, delta t is 0.5, so I get 4. And then I'm going to calculate my new t and my new y by looking at the old t plus delta t. So my old t was 0, delta t is 0.5, so I've got 0.5 here. My old y was 10, and now I have a change in y of 4, so that's going to be 14. Now I calculate dy dt using these two new values, 0.5 for t and 14 for y. So it's going to be 1.5, that's my t plus 1, times 14 minus 2, which is 12, and you get 18. 18 times 0.5 is 9, that's my delta y. Okay, so my new t is my old t of 0.5 plus my delta t of 0.5, which is 1. My new y is my old y of 14 plus delta y of 9, which is 23. Now I'm going to plug into the formula for dy dt. T plus 1 is 2. 2 times 23 minus 2 is 21. So 2 times 21 is 42. 42 times a half is 21. New t, 1.5. New y, 23 plus 21 is 44. Plug into the dy dt formula. So I have 1.5 plus 1, that's 2.5. Times 44 minus 2 is 42. So I get 105. 105 times a half is 52.5. And then I calculate my new t, 2. New y, which is 44 plus 52.5, 96.5. And I know that's where I want to stop, because that's what I was asked to find the y value when t is 2. So here I have a t value of 2, and here's my y value, 96.5. To write this in function notation, we would say that y of 2 is approximately 96.5. Okay, on the slope field above, now draw a rough sketch of the approximate solution on the interval of 0 to 2. This graph will be piecewise linear because I'm going to use these numbers that I got using Euler's method. Okay, so I have my given, well, I'm using these t, y values. I'm going to plot each of these as points, connect them piecewise linear. So I start with 0, 10, about right there. And then I have a half, 14, and then 1, 23, 1.5, 44, and 2, 96.5. To almost 100, something like that. So piecewise, then we're connecting these with lines. The slope field indicates that they're curved, but these are the only points I calculated using Euler's method. Okay, so now I want to calculate the exact value of the solution so that I can compare it to what we just got approximately. So I'm going to use separation of variables to get it. So I'm going to move the y minus 2 over. So I have 1 over y minus 2 dy equals t plus 1 dt. Integrate, integrate. So I have the ln of y minus 2 equals t squared over 2 plus t plus c. E to both sides. So y minus 2 equals c e to the 1/2 t squared plus t. Add 2 to both sides. And then I can solve for c by using my given initial condition that y of 0 equals 10. So 10 for y, 0 for t gives me c. E to the 0 is 1, so plus 2. So c is 8. So my solution is y equals c e to the 1/2 t squared plus t. Oh, whoops, I forgot to replace the c. 8 plus 2. And then I want to find the value of y of 2, right? Because that's what I estimated using Euler's method. How does that compare to the actual y value when t is 2? So I'm going to put this all into a calculator. 8e to the 0.5 times 2 squared plus 2 plus 2, and I get 438.7 approximately. How far off is our estimate from the exact value? Pretty far, right? Our estimate was 96.5. So Euler's thought y of 2 was approximately 96.5. Exact y of 2 is 438.7. So that's pretty far off. How could we improve our estimate? Smaller delta t, smaller step size.